Professor Cong is the Rudd Family Professor of Management at Cornell. He has worn many, many hats. He's the founding faculty director for the FinTech Initiative at Cornell. And he is also involved as a faculty scientist at the Initiatives for Cryptocurrencies and Contracts, and also a research associate at NBER. As you likely know, since you signed up for this webinar, his research really focuses on financial economics, information economics, fintech, economic data science, entrepreneurship, and issues dealing with China. His most recent work, which I'm sure he will touch upon here, has focused on the intersection of technology, data science, and finance. Will is really prolific in his research, and that research has been very far-reaching in its effects, both within academia as well as fintech organizations and investment firms. Way too many for me to list, but yeah, if I could choose anybody who has done more significant research for this particular current time, or that is really applicable to the world, really, I could really choose nobody better than Will today. So Will, thank you so much for joining us. I'll hand it over to you.
Thank you very much, Michelle, for the kind introduction. It's a great honor to be joining you for this webinar and just share with you a research agenda that my co-authors and I have been pursuing for the past, I would say, 4 or 5 years. That has been quite a while. And I as Michelle was saying, I really think the field of digital economics and financial technologies are going to be with us as a mainstream topic. There's a lot that's going on. And more importantly, there's a lot that economists, especially financial economists, can contribute to the field. And so hopefully this talk is going to be informative as you develop your own research agenda and research projects. I'm sure many of you have been following what's going on in the kind of AI field, and ChatGPT, Llama, Baichan, Cloud. There's a lot of open source, open AI models. They are typically referred to as large language models. I'm not going to talk about textual analysis or language models, but I want to talk about large models versus sparse models. I think by this point, most of us are convinced that large models are very powerful, they're robust, they are very effective. But as economists, there's a reason why we wanted sparse models, right? We don't want too many factors, say in asset pricing models. We want the model to be, easily estimated, and more importantly, we want the model to be interpretable. As economists, we need to understand what's going on behind the, within the black box, and that makes that leaves much to be desired with all these large models. So today I hope to talk about one direction about sparse AI models that are just as effective as large models, yet they are very interpretable. I'm very excited about it. I'm going to base the talk on these 3 papers, and I'll introduce them one by one. Okay, so let me just provide a really quick background about why we need machine learning or AI models. And to many of you, this is not unfamiliar, right? Our financial data or even economic data in general really involve high dimensionality. And there's a lot of work being devoted to dimension reduction. When we run a penalized regression, for example, we are reducing their dimensions. And the relationship behind our key variables could be highly nonlinear. And that's why non-parametric models or deep learning models using neural nets would be helpful. Now, these two are shared in science and engineering as well. In social sciences, though, we do have a lot of endogenous variables that interact. And that means we are not typically facing sparsity issues, actually facing endogenous interactions. And that would make regression trees or classification trees very attractive, because they are shown to capture interactions very well. And we also have low signal to noise. For a reason, if a signal is very informative, people will trade on it. Financial markets do have this forward-looking nature, and that means informative signals will become noisy over time. And we just have to be very careful with out-of-sample metrics to help us assess the performance going forward for many models. In addition, our existing econometric tools for extracting time series information is actually quite limited. When we talk about the Riemann Gauge arch, they all assume some sort of stationarity or metastationarity, which is fine. I'm not saying machine learning models don't assume that, but they are a more flexible class of models that would allow us to extract more information in the time path. And that's what the latest AI models are about. But if you are familiar with our asset pricing literature, you probably realize that we spend a lot of time extracting information in the cross-section. And that's not something that off-the-shelf AI models are going to do for us. They are typically dealing with a single sequence. In fact, they are referred to as sequence modeling. It's essentially the neural net version of time series analysis. And the typical AI models who just do one single sequence, think about machine translation. You're just reading the essay sentence by sentence. So if you want to extract more cross-sectional information, we have to modify the model. We have to tailor the model for financial applications. And that's exactly what we are going to do. In addition to these statistical features of financial data, we also have to have good economic motivation for using certain machine learning or AI tools. And we want interpretability for many reasons. Say you run a fund, out of fiduciary duty, you still need to explain to our clients roughly what you're doing. You can't just tell them, I'm developing a strategy from a deep neural net black box. That's not going to be satisfactory. And if you worry about distributional shift, regime switches, transparency of the model is still key. So if we look at how machine learning models have been applied in finance, in the asset pricing area, we've used a lot of the off-the-shelf machine learning models that were developed for pure predictions. They do not include any economic structures. And there are attempts to impose economic structures, such as no arbitrage, such as a factor pricing model. And so far, they are mostly using supervised learning. And as I'll show you, all the papers I'm going to touch on are using neither supervised learning nor unsupervised learning. They are really under this broader theme of goal-oriented search. All you need to do is to specify a goal and do a clever search within the large modeling space. So it's neither supervised nor unsupervised. I'll come to that in a bit. In corporate finance, the applications so far have been even more limited, right? There's a lot of work on textual analysis. I'll say, if you touch on the AI models, they're mostly about word embedding models or topic models. And lately we have transformer-based large language models, such as ChatGPT. And beyond textual analysis, there are some applications of machine learning to predict certain corporate outcomes, but it still stays at the prediction exercise. Now, what we want to do is we're going to modify the models from the AI field, or sometimes even develop the models ourselves in order to answer core questions in both asset pricing and corporate finance. Now, what is so special about AI? I really want to emphasize what we are going to look at are beyond basic machine learning models. Most of the basic machine learning models are typically used for supervised or unsupervised learning, but that's not the core theme in the latest AI development. And when I say latest AI development, I really have in mind, AlphaGo, self-driving, machine translation, large language models. They use something very different. And if you look at the kind of development of AI over decades, we really went through several stages, automating physical processes, automating computational steps, in the case of calculator or a computer. And lately, when we talk about AI, what we are doing is really automating the process of searching for a very satisfactory solution in a large modeling space for very complex problems. That's why we call them intelligent. As I said, I'm going to call this goal-oriented search. Now, and if you think about machine learning and neural net models, these are just flexible models. And when we make them flexible, what are we doing? We're enlarging the modeling space in order to describe the world better, right? In terms of explaining outcomes or making predictions or recommendations. But the space is so large, to search for the optimal model is a very demanding task, sometimes impossible task, given current computation power that we have, even though computation has been improving over the past 10, 20 years. So the search has to be done cleverly. And what the AI field has been doing is heuristic search using deep reinforcement learning. I'll come to that in a little bit. And I'll show you one example of applying that to portfolio management. That's one way to go. And the other direction, which my co-authors have been working on, is greedy search using trees, but not the plain vanilla classification or regression trees, because they were not designed for finance problems. We have to modify them. And I'll explain what I mean by greedy in a little bit. Now, for the popular AI approach from computer science, reinforcement learning is what's behind ChatGPT, AlphaGo, so on and so forth. The idea is you can give me any economic goal. As long as you can formulate the goal as cumulative reward, we can do an optimization of the cumulative reward. And the policy recommendation would be the solution for this problem. In the case of managing a portfolio, right? You tell me, I want to maximize returns over the next 12 months, or Sharpe ratio, auto-sample Sharpe ratio. I want to minimize the variance of my portfolio. The algorithm is going to help you to search for a portfolio strategy that's going to optimize this. I'll be more specific on that in 2 slides. But for greedy search, what we're really using is trees, or tree-based models. Why do we call it greedy? Well, trees are ways of partitioning the covariance space to cluster observations. So after we make the first split of the observations, right, we continue splitting it into branches and leaves of the tree. When I'm at the 4th split, I don't go back and think, oh, what if I did something different for my first split? If I think about that, there are too many permutations and combinations. But because I fixed my first split and then move on to my subsequent splits, it is greedy. And the concrete example I'll give you is portfolio sorting. Right? Traditionally, we do double sort or univariate sorts, but why stop at double sort? Why, why don't we go beyond triple sorts? And when we put many univariate sorted portfolios together, we're allowing a lot of information to overlap. And in fact, that's very hard to create test assets that span the efficient frontier. That's a big challenge for both asset pricing models and just think about investment practice. And using trees, you can have a systematic way of sorting asset returns into different portfolios that hopefully better span the efficient frontier. But to do that, if you think about all the characteristics we observe, there's a lot of permutation, and computationally, it's just too hard to do. And that's where greedy search is very helpful. Now, trees have a few other very desirable properties, such as it's very interpretable. You know exactly how to create the leaf portfolios. You know exactly how various inputs, be it firm characteristics or macroeconomic variables, interact to create these leaf portfolios. Trees deal with low signal to noise very well. And in many cases, in other fields, that has been demonstrated to be better than deep learning models in many cases. And if you are a statistician, you probably care about asymptotic properties, right? Convergence. Those are very hard to prove for neural nets, but they are relatively straightforward for tree-based models. So I'll come back to that. But let me start with a quick example of heuristic search through reinforcement learning. What is reinforcement learning? Reinforcement learning is essentially you take an action, you interact with the environment, and then you'll get feedback, right? I would say that's how we actually learn many things. And if you think about corporate finance decisions, right? Managers taking an action, and they also get feedback from the market. There's a big literature on feedback. So reinforcement learning is approximate dynamic programming. It's not going to be the focus of today's talk, so I'm not going to go into details. I'll quickly mention this paper that we actually first wrote in 2019. That was I think the first large model, relatively large model in finance. We had over 10 million parameters. It's not very large compared to ChatGPT that has a few hundred billion parameters. It's a large model, probably the first large model in finance. It's the first application of transformer combined with reinforcement learning. And transformer is the T in ChatGPT. So, there are more details and philosophies behind this approach. But I just want to quickly motivate the application of reinforcement learning in portfolio management. Right? We have to start with an economic question. And the economic question we have is, if you give me an arbitrary portfolio management goal, can I do better than what the literature has done? Right? The literature has approached the problem using a two-step approach. You estimate the pricing kernel, you try to minimize pricing errors and all that. And then in the second step, you construct portfolio, right? If you give me the estimates of the first two moments of expected asset returns, I can do mean variance optimization. But if we take a step back, the two steps are not always aligned in their goals. If I want to manage a long-only portfolio, let's say I want to maximize Sharpe ratio or some cumulative return, I already know one asset's expected return to be super negative. Right? Yes, I care about diversification and the variance, covariance, but that asset is not going to be in my portfolio. I have a long-only portfolio. And do I care about pricing that asset's other moments very accurately? Well, if I care about asset pricing, yes. But if I'm just thinking of optimizing my portfolio based on limited data, limited statistical power, I actually don't want to spend my limited statistical power to figure out how to price that asset very accurately, right? So you can already see the goals are not always the same. It would be much straightforward to do a direct optimization of my inputs and the portfolio strategy. We were not the first one to do it. Michael Brand and co-authors have done more than a decade ago. But over there, either take a non-parametric approach, but then that approach was limited by the high dimensionality of our data. You can't go beyond 2-3 dimensions over there. Or you take a parametric approach, but then you are subject to misspecification in the intermediate step. When you write down the order equation and all that, if you write down a consumption asset pricing model or framework. And that's where deep learning is helpful. Right? We have deep neural nets that allow us to handle the high dimensionality of data, right? Nonlinearity, so on and so forth. And then we use reinforcement learning to optimize the objective, which could be arbitrary. Now, there are more details to this paper than I have time to cover. If you're interested, I definitely encourage you to take a look. But here's the architecture of a portfolio model that we develop. The idea is you can input asset time series information. Right? It could be book to market over 12 months, number of employees over 12 months for each asset, asset I in the superscript. You pass that piece, raw data into what we call a sequence representation extraction module. Transformer encoder is one example. You can use long short-term memory, other forms of RNN, recurrent neural nets. That's fine. These are off-the-shelf modules that you can take. You pass that through the deep neural nets, you get a representation of the time series information in the asset. And what we did is we added a cross-asset attention network. That's essentially the self-attention used in machine translation. But instead of applying it in the time series, you apply the structure in the cross-section. To further extract information in the cross-section, you get a what we call a winner score. And then, based on the winner score, you can construct portfolio. High winner score means larger long positions. Low winner score will be large short positions if you're doing a long short portfolio. And then you can see how the portfolio is doing. If it's doing well, you search more in that parameter region. If it's not doing well, you search away from the parameter region. That's where the economic goal and reinforcement learning will be relevant until the model converges. That gives you very good performance. And in our case, if you look at, if you have auto sample Sharpe ratio as an objective, you can consistently get Sharpe ratio above 2, sometimes close to 3, after excluding small and liquid stocks, and you can control for various risk factors. In the paper, we impose a number of economic restrictions, and the results are still quite robust. That's just performance. What about interpretability? This is not a sparse model. Well, it's very challenging. We do a number of things to interpret the model. But the truth is, with large models, with deep neural net-based models, interpretability is just a challenge. You just don't see a lot what's going on behind the model, right? Within the black box. That's where I want to move to tree-based models, because they provide sparse models where you don't have many parameters. It's still relatively low dimension in terms of representation, and yet they work almost as well as deep neural net models. And here is the first example. We had a different title earlier, growing the efficient frontier on panel trees. I'll tell you what panel tree is, but again, let's start with an economic question. And this is related to the example I was giving, right? Sorting portfolios. We typically just do ad hoc sorting. Pick a characteristic, do univariate sort or double sorts. But let's think about doing this systematic. And by the way, why do we want to sort assets? Well, in many cases, we want to sort them into portfolios, basis portfolios, right? That can serve as good test assets, that can help us to build asset pricing factors, latent factors in many cases. And there's actually limited study on creating test assets. Now, again, trees have many advantages, right? That I mentioned earlier. What is the drawback if you just take a off-the-shelf tree-based model, let's say CART? Number one, it's not even designed for creating test assets. It's designed for prediction exercise, right? If you want to predict or minimize asset pricing errors, you can use a tree-based model. But then tree models, plain vanilla tree models, assume the returns to be IID over time. And we know that's not true. So tree models are essentially single period models. They don't really handle panel data. So number one, we need to modify that. Not too difficult, right? You can have vectors, a time series of returns as input instead of a scalar as an input. There are ways to incorporate time series information in order for trees to handle panel data. That's one modification we did. Trees grow locally. What I mean by that is when you have a parent node of observations, you split it into two child leaves. The criteria is typically based on, let me see if I have that. I didn't include it here. It's typically based on, let's say how well it fits a constant in the, let's say we're predicting asset returns, right? We can use two constant kernels in the leaf, in the two leaves to minimize the pricing error. But then when we think about this particular split, we're just using data within this parent node. We're now utilizing all the data. And what's the issue with this local split criteria? Well, as the tree grows, you have less and less observations in each branch. And that's when noise start to in. So tree models overfit in many cases. The way we deal with that overfitting traditionally is to use a ensemble. Right? You have many trees together, random forest. Right? I superimpose 500 trees to have my forest. That works great because you average out overfitting. But then the downside is, well, we no longer have interpretability. I have 500 models put together, so I don't really know what's going on. Our goal is to use single trees so that they are still very interpretable. Yet we want to guard against overfitting. How do we do that? Well, the way to go is to introduce a global economic criteria to grow the tree. And I'll be more specific on that. Because the economic criteria we impose involves all observations, not just about the node that we're splitting. It actually guards against overfitting. Okay, so that gives us interpretability. Another disadvantage with plain vanilla tree models would be that if you use ensemble, you lose interpretability, as I was saying earlier. Okay, coming back to this portfolio sorting problem. Suppose I have all my observations in the root node, return observations. I can try a candidate split. Here, I'm splitting the observations along standard deviation of dollar volume, right? And let's say you standardize it in between -1 to 1, then 0.2 will be, the 60th percentile. You can, basically the trees would search all possible characteristics and all possible split thresholds to maximize some split criteria. And this is one candidate. Suppose I do that split, right? And I come to my second split. I try, market equity, basically market cap, industry adjusted. You can try something different. That's fine. That's the search process. Suppose I try a candidate for the second split, and the first split is already figured out. I get these 3 leaf portfolios. What we can do is we can introduce the global split criteria to be, I want the 3 leaf portfolios to span the efficient frontier the best. What you do is you create a mean variant efficient portfolio out of the 3 leaf portfolios, right, to maximize Sharpe ratio. That could be the global goal. Or I can say, well, let me just construct, let me just use that mean variant efficient portfolio to be my latent factor after 2 splits. The superscript 2 means 2 splits. I want that to price all individual asset returns well, so you minimize the pricing error. That's fine. The economic goal is up to our definition, but you need to let me know a goal. Once you let me know the goal, I can split the observations into leaf portfolios in order to maximize that goal. And in our exercise, we maximize one criterion that we use was to maximize the Sharpe ratio of the mean variant efficient portfolio of our leaf portfolio. And when we do that, well, actually, I'll come back to the tree structure, exact tree structure. When we do that, we actually find we can span the efficient frontier much better. One thing I want to note is you can generate factors from the tree. One single panel tree, one single P tree gives you one factor, but you can use the idea of boosting to generate multiple factors. You pass all the returns through the tree, take the residues, pass the residues through a second P tree that gives you a second factor. You can also take the residues from regressing the returns on some well-known factors, such as market, and then pass it through a P tree. It becomes a market-adjusted P tree model. So it's very flexible. Now, we tried this on U.S. equity and U.S. corporate bonds. I'm just going to show you results from U.S. equity. Very standard inputs, the usual suspects. You have training test samples and so forth. That's fine. This is the basic tree structure. What it tells me is, in a data-driven way, I'm learning from data that a few characteristics interact to explain the cross-sectional return the best. And in this particular example, where I think this one we maximize Sharpe ratio, the data are telling me idiosyncratic vol, right? Volatility after controlling from a French three factors, as well as earnings to price. These two characteristics are the most important in explaining the cross-sectional returns. And the criteria that we were using was to maximize the spanning of the leaf portfolios, right? And here we have 1, 2, 3, 4, 5, 6, 7, right? Less than 20 leaf portfolios. We can look at how well they span the efficient frontier. And by the way, that also gives us good investment portfolio, right? If you have high Sharpe ratio, and if your portfolio's goal is to maximize your Sharpe ratio, the trees actually work pretty well. Auto sample, you can get Sharpe ratios based on the investment global lead criteria. You can get auto sample Sharpe ratio close to 3. And how does it compare to other models in pricing individual assets? You can also look at that relative to well-known factor models, even latent factor models such as IPCA. It's doing quite well out of sample in pricing both individual stocks and portfolios. I wouldn't claim it's the best performing, but it's in that best performing category. But what's more important is it's interpretable. None of these models, you can give me a PCA-based method, it's not interpretable. You're combining hundreds of characteristics. And here you only need a couple of characteristics to understand the cross-section of asset returns. You can do more. You can split across the macro variables in order to figure out what macro regimes would make certain characteristics more relevant than not. You can use the interaction learned from a P tree to enhance and resurrect your trading strategies. Right? Some trading strategies seem to have been traded away. But if you do a double sort, right, interact with the correct characteristic rather than just using size as a second sorting variable, you probably can recover the anomaly. And that's very relevant if you manage a fund as well. So that's one example of using a tree-based model that's sparse and interpreted in order to solve a sorting problem that's very important in asset pricing. Now, that's still thinking about a common pricing model for all individual assets. A second application that we did with panel trees is to think about grouped heterogeneity. In the case of asset pricing, what that means is, well, we know the factors that price corporate bonds are different from the factors that price equity in many cases. We know the factors that are relevant for pricing the Chinese equity market are different from the factors that price the US equity market. So, but for that, the grouping of assets are given exogenously, right? We use country, we use asset class, you can use industries. So our question is, suppose there are these latent grouped heterogeneity in the panel data. Can we have a data-driven way that's economically guided that would naturally group assets or observations into these heterogeneity groups while still maintaining sparsity of the model, right? We don't want a full factor zoo in asset pricing, for example. And by the way, this is related to incidental parameter price and how we cluster standard errors as well. But when you think about clustering standard errors, that's just a very restricted space of clustering. Like here we're thinking about a different space for heterogeneous models for these observations with group heterogeneity. So very abstract. Let me come to this example of asset pricing. It's probably going to give you more concrete ideas here. So we know we have many struggles or bottlenecks in factor asset pricing. And the reason we don't want too many factors is we still want the model to be sparse. And but in a recent econometric paper, several authors show that sparse models are not working great. Large models or dense models are working better. So we kind of want to take a mid ground there, right? We want it to be large enough to be very powerful, right? And yet it's small enough to be interpretable. So let's think about how we approach standard factor modeling in asset pricing. Right, we have asset returns on the left-hand side, and right-hand side we have these factors. We put a lot of stress on the right-hand side, trying to figure out the right factors and so forth. Our idea is, okay, let's do a bit more on the left-hand side to grouped assets that have similar kind of asset return structures. That would help us to reduce the burden on the right-hand side and to have a sparse model that explains asset returns. So the exercise is to jointly cluster observations and estimating a heterogeneous factor model. Basically, instead of having a common factor model, we'll have an uncommon factor model. And the question that the model really speaks to is what factors price what assets and when, right? All these are going to be data-driven under an economic structure that we impose. So that's the exercise. When we apply this, we call it Bayesian clustering model, BCM, but it's a formal panel tree. When we apply it to asset pricing, that's what we can do. So why do we need a Bayesian model? Again, in the interest of time, I'm skipping many details. We are not using a Bayesian framework to cluster the observation to grow the tree. The tree is not Bayesian in that sense. But once we grow the tree, we have observations in each leaf node. We use a Bayesian approach to select factors. So within each node, we estimate a factor model that's sparse, just involving very few factors. But we use Bayesian variable selection. In particular, we use spike and slide prior. Again, there are more technical details to it, but you can think about this as the Bayesian equivalent of lasso, right? You're just selecting some variables. But why do we need a Bayesian approach here? Well, it turns out there are many benefits to the Bayesian approach. You reduce model and parameter uncertainty, and incorporate economic prior belief on the relevance of factors and so forth. But the most important reason for us to use a Bayesian approach is that we can then use likelihood as our lead criteria of the tree. It's going to be very natural. So here is how it works. We have asset return observations from the node, we start to split the observations. Let's say after 2 split, you have 3 leaf portfolios. I'm trying to decide my second split, right? I could split the left child node using market cap at certain threshold. I could also split the right child node into 2 leaf nodes, right? N6 and N7 using, let's say, stock variance. These are just split candidates. How do I know which one should I split? Well, what you can do is you can calculate the marginal likelihood after fitting a Bayesian variable selection within each node. And the way you combine them into a global criteria, split criteria, is to multiply it, right? Because after multiplying this marginal likelihood, you just get a global joint marginal likelihood. And you want to maximize the global joint marginal likelihood. You want to maximize the probability of observing these SI return outcomes after you estimate the heterogeneous factor models for each node based on certain splits, right? So on the left-hand side, I can calculate this likelihood. Right-hand side, I can calculate this likelihood. Whichever is higher, I'm going to pick that split. That's how we grow the tree. Now, if you use a frequentist approach, let's say you use lasso selection of variables within each leaf node, you have a hyperparameter to fine-tune your lasso selection, right? A penalty parameter. How do you combine them across different clusters of observations? That's very hard to do. Do you add them? Do you multiply them? There's no natural way of doing it. And that's where Bayesian approach is helpful. You can always define marginal likelihood. And the way we combine them is to multiply them. It's still a marginal likelihood. Again, in the interest of time, I can't go into details, but I want to show you some exercise that you could do once you apply BCM, say to US equity data. And here, we are looking at, let's say, 20 factors as the factor pool. We're going to select from the 20 factors. You can do more. Computation-wise, it's going to be more costly. Each additional factor you add in the Bayesian framework is going to double the computation. Anyhow, so when we look at the SI returns, this is the tree that's grown. Basically, the data are telling you that the 2 variables that are most important in splitting observations into different clusters, so that each cluster may have very different factor pricing structure, are stock variance and market cap. So it basically splits all observations into these 4 bins. Their pricing structure are going to be quite different. And in fact, you can explain many anomalies by this group heterogeneity. So they are not anomalies. When you properly group observations, they can be priced. You can also get rid of many factors. There are not really systematic exposure to risk. There are just some interactions of characteristics. There are manifestation of grouped heterogeneity in the return observation. You can do all those exercises. You can look at what is truly common across SI return clusters. And what we found is market and size turned out to be very common across different clusters. But other factors are not as common. They're heterogeneous. In fact, there's one cluster that we just can't price. There's no factor, well-known factor, or common factor that's selected. And if you look at that stocks, look at that particular bin, I think it's N56. It involves stocks with high volatility, low earning price, small, it's essentially the junk stocks. So what the model tells us is also what type of assets can our typical factors price, and what type of assets that are that will be just too hard to price with our current set of factors. That's useful for practitioners, at least, right? When they think about should I go into areas where I know I have a pricing structure, pricing model that works well, and or do I want to be exposed to, a lot of unknown uncertainty? What the model does, again, right? This is the asset pricing model. We have to show asset pricing performance, and here skeptic and agnostic are just different based in priors on how relevant the factors are. A skeptic would have a prior that says most of the factors are irrelevant. Data has to convince me that they are relevant. Agnostic would be, I'm open to the possibility that all these factors have some relevance, and I'm going to update from that. And what we learn is for some cluster of assets that are endogenously revealed through this BCM model, you can explain the auto sample R-square over 24% of the R-square. Whereas typical factor models can only do 10%, 11% maybe. So this is a huge improvement in explaining the returns of certain asset groups. And the key is what assets make up the group. And that's what the model tells us. And so it tells us about priceability and the group composition. You can do more. You can include macro predictors. So basically, if you make the first few splits macro variables, what you learn is using macro variables, you can predict regimes where certain factors are more relevant. For example, what we observe is the aggregate stock market volatility and earning to price ratio, basically some valuation metric and volatility metric, are already sufficient to help us to predict several different regimes featuring very different factors that are relevant. So I don't have that figure here, but in the paper we do show in calendar time how the regime switches back and forth. And what we find is a market is a frequently selective factor along with idiosyncratic law, and these are actually quite consistent with the earlier panel tree model. And this BCM model, another way to view it is, we've seen papers by Titman, by Kent Daniel, teaching for characteristics against factors, but that's typically done in a linear fashion. The BCM model here is a way to think about how you can combine information in characteristics and factors. The information from characteristics basically tells you how asset returns exhibit grouped heterogeneity that help us to group asset returns. And then the factor information help us to price the cross-section of returns within those clusters, right? So in a nonlinear way, you can have very deep and nonlinear asymmetric interactions. That's what trees are very good at. But taking a step back, the bigger picture is, these panel tree models are greedy search in the joint space of security sorting and heterogeneous factor models. Neither supervised nor unsupervised, but it's guided by an economic goal, right? That's the common theme. So just coming back to this overall idea, I have some ongoing work with my colleague at Cornell and student applying this goal-oriented search of the finance, which I didn't have time to talk about. But safe to say that learning and searching in a large modeling space by interacting with the environment or using greedy algorithm is a very common scheme in AI. And that scheme is very relevant for financial applications, but we have to tailor them for our own economic questions. in mind. And today I focus on tree-based greedy search, goal-oriented greedy search, to study asset pricing model, whether you're focusing on creating test assets, generating factors, or think about heterogeneous factor modeling of asset returns. Okay? So what it really gives us is both performance and interpretability. Because if you look at the tree, it's still very sparse, right? It's just definitely less than 50 parameters or characteristics, as compared to the large models. Usually get once you get over 1 billion parameters, it's no longer trainable by our typical university servers, and that's problematic. Because if you use an open sourced large model, you really don't know what goes in the pre-training. You don't know how it gets updated, so on and so forth. So, sparse AI models is a good balance. It gives you interpretability. You can still be in control of the training of the model, and its performance, at least as I illustrated in the case of asset pricing, are as good as many large models. And this space is wide open. We are probably the earliest to expand this tree-based structure, but there are other ways to build sparse AI models. So I'll stop here to take some questions from the audience. It's actually from Prof. Rao about one problem with asset pricing is that we don't have a good theoretical justification on why some factors are important and which ones are not, and when. So in a way, these models might help us to identify which factors are important, but they can't help if we don't have a good theoretical justification. That's a great question, actually an important issue, not only for the tree-based models, but for reinforcement learning that I was talking about earlier, right? These are still very much data-driven models. The tree models are still interpretable, so it kind of gives us some idea on how certain characteristics interacted, so on and so forth. The deep learning models are even trickier, right? You don't even know what exactly is going on other than seeing the outcome. But I think what they can do to help us understand the fundamental theory is they can help us uncover certain patterns in the data that would probably lead to further theoretical research. Just like in the early days, right, when we see size anomaly, value anomaly, there wasn't a clear theory, but once that's the established regularity empirically, people start to work more on theories explaining that. So that's helpful. Another way they can be useful with our theoretical research is you can actually incorporate certain theoretical results into these models. One example is suppose you really like a structural model, you calibrate that structural model. After that, you use that to simulate and generate data. Then you take the data to these machine learning AI models. But in a way, there's some transfer learning and retraining going on. But you can kind of pass some knowledge from theory models or earlier empirical models into these models as well. So the space is wide open. I think there's a large variety of ways that we can utilize these tools.